So what we are going to focus here is the requirements and what these requirements brings us the challenges because these requirements are not straightforward. There are many elements, many components involved, and they are all interdependent. So that brings us complexity and challenges, and that is where we see a lot of opportunities in electric drive unit. Now, the key four elements in powertrain, electric powertrain, is battery, machine, inverter, and the say gearing or a transmission which connects to the wheels. So in this presentation, what I will focus, we will not cover battery as such, but some of the elements or some of the parameters where we have to touch base, we will cover those from battery perspective. But battery as such component we will not cover. So that is the scope of the today's talk. So what agenda I have today is very simple. It's like we will start with some requirements, especially the performance requirements. There may be so many other requirements, but we focus on performance. And what elements we will be majorly focusing is transmission, machine. What we are going to look at is the performance requirements. And for electric drive unit, as I mentioned, the what it covers is so there are some key elements or key parameters associated with these three components: the vibration, maybe speed and torque characteristics, modulation strategy. These are some, say, just to name few. These may be our say high level parameters. So just I tried to put some few of them, and then there is thermal consideration for all of three elements. So the along with this, what we will be covering is what would be the, yeah. So the thing is the what we can expect. I mean, what you can expect from this webinar is we will touch base upon some key parameters and how they impact on EV performance. This is not a deep dive, but this will give us a very good high level view on these parameters, and we can then later deep dive those and some functions of those parameters we can go. So what I am trying to do here is put some slides on each component, or share some information on each component like inverter, gear, and machine. But what happens is when we talk about one component, there are elements associated with some other component, say, okay. So it is very difficult to isolate one component and just talk about it. So you will see some mixing or some kind of a dependency coming into picture when I talk about, say, inverter. There may be some discussion on machine. So vice versa. So the thing is, we will be trying to put component focus, but also we'll try to break those silos whenever required. So a very high level before we come to the vehicle performance requirements, the why we will see why electric machine or electric drive as such is a natural choice. Because if you see ICE and gears, the transmission, what we want from that as a vehicle is this kind of torque speed. What we get here is a torque speed curve like this, and that is what vehicle demands. And the good part that electric drive has is naturally it gives this kind of a characterized torque speed curve, which vehicle ultimately calls for. So of course we need gears, but we can definitely may not need so many gears. But the point here is it's becomes a natural choice that which can cater to this kind of a specific vehicle requirement, which is very high level requirement. And that is where you see the electric drive unit become our focus point, because that is where we are going to replace our IC and transmission with our maybe new transmission and the electric machine. So this is equivalent to our IC engine, and this is what is going to propel with the support of the energy and the power from the battery. And that is why we are discussing and focusing more on the drive unit as such. So and it is a natural choice. It's a characteristics are very much close to that. Now before we as I mentioned, before we go to the vehicle level requirements, there are targets set by Department of Energy, and these are revised now. If you see year wise, they have set. It is up to 2020 they have defined. So there are various densities, volumetric densities, and some dollar per and the cost. So these targets are enable. I mean, these targets are set to enable the EV more, feasible to adopt, or more, say, cost effective in terms of say also in terms of weight and volume. So there are separate targets. You see power electronics and motor. So when I say power electronics, let's say it's a inverter, because that is where we are focusing, but there can be converter, as you know, inside that, and then there can be onboard charger, OBC, on the vehicle. So these targets are very directive. It gives directions, and it gives us opportunity to move in this direction. But they have revised this, because most of the targets in industry are either surpass, or we are very close to these targets. But the challenge, even when I say these targets, is apart from cost, we are very close. But the cost is still we are struggling, and there is a lot of research going on, and these are some of the challenges which is posted by the DOE, Department of Energy. And you can see here there are variety of these components are put down, and those key research areas are high level topics are mentioned. So if you are associated with any of these research areas, maybe this can be a good direction for your work, or you can consider them for your further work. So these are very high level targets, requirements, which are not, I mean, which is indirectly has to do with the vehicle as such. So what about the cost? Which part of the which parts in the component that we have to focus? So if you come to the machine, here I am taking IPM machine, interior permanent magnet machine, which is more popular. The magnet is the expensive part. If you consider induction machine, maybe the winding, the copper is the expensive part, because then rotor is aluminum. So you can consider that aluminum cost is more here, and in case of induction, and in case of PM machine, if you are using, say, rare earth magnet, then it is a 53% or close to 50% cost is coming from that itself. So it is similar to our battery. If you put the full vehicle, the battery cost is almost 50-60% of the total powertrain vehicle. Then this is how the magnet is equivalent to in just if you consider machine. If you come to the inverter, power electronic side, the switches and the signaling circuit, your drive circuits, those will be a very expensive one. The next to the capacitors are those bulk capacitors, right? Bank, 40%. So those 2-3 elements consume a major portion of the cost. If we put all this together for our electric drive unit, you can see the transmission also equally plays role. Power electronics, transmission, and a machine. So this is how the total pie chart will look like. So the key components here are these three, which will be the major contributors in this electric drive unit. Now, where we stand today, like one of the example that I could see here is a Delphi inverter. Against those DOE targets, they have published their own numbers. So there are many other companies that they have published like this, and they take these references so that we can compare, or we can say check those how they stand, where they stand, and you can see the cost is made, that is so called, The specific power density and the volumetric densities are also met or surpassed. But what we have to see is ultimately the landing on-road cost of this inverter. This is a component, like some caveats are there, like some volumes and numbers. So we cannot directly take this as a input, but we get some direction from this, that we are heading in right direction, and the cost is also becoming a little viable. We are still not there, but we will be there for sure. So what is the first thing that comes to the mind when it is a vehicle? So coming to very specific to that vehicle, those all what we discuss is a high level target, may not be really dependent on the vehicle that we are considering. But the drive cycle, the moment we come to the vehicle level, drive cycle is the key element. And based on, so this is a torque, speed, and efficiency plot. And what we will be doing, this is called heat map, and we will be plotting those drive cycles on these torques curves. So what this gives us a residency or a density where these points are dense. We can focus on those areas, or we can focus optimizing some our system in this direction. Okay, so it gives us all the operating points. If we put this in a little better fashion, to see, you can see on this chart, for highway driving, you can expect that, okay, you need full range, full say spectrum of your say speed you have to operate. The vehicle will operate, and we have to put our electric drive in it, considering that. For a city drive, we may end up in this kind of a residency. So what we will be considering as to start with is what all drive cycles we have specific to India, specific to our driving styles. So each OEM will have their own key drive cycles, their own drive cycles, rather than the standard whatever you call WLTP and other NEDC. Those cycles are standard, but there will be our own, I mean, their OEM will have their own realistic cycles, which will be the starting point of discussion. So this is where the electric drive unit is also shaping up, because it is deciding how much power we need, what is the top speed we need, what that top speed converts to the maximum speed of the machine, and what acceleration we want, how long we want to sustain that acceleration. Okay, so all these elements are decided at this stage. And the key thing that we as a electric drive people, we can say, we will get some idea that, okay, where we should be focusing for optimizing our design. As a system integrator or as a component designer, we have to decide where I can focus my design. So let us again continue our discussion on this torque speed curve and try to plot various requirements so that we can shape this torque speed curve in a better manner, or we can derive some specification out of it, so that we have a component specification from this torque speed curve. So when we talk about acceleration requirements, like I need 0 to 100 kilometer per hour in say 5 seconds, that particular requirement or that specific requirement will dictate this peak performance. How long in the sense, how much speed I should have this constant torque. So we call this as a constant torque region, and this is a constant power. The torque starts reducing, but you can say the power may be little bit steady here. It starts dropping later in a realistic torque speed curve, but we define this as a constant power region because the torque is dropping but the speed is increasing, so you have a power there. And then this, once we have this peak performance, which may be for 10-second 5-second kind of a duration, then we talk about the continuous performance as well. So the continuous performance may be like you have to define, say, what kind of a gradability or what kind of a continuous slope vehicle can climb. So the realistic curve may look like this instead of flat, say straight line of this constant torque. In continuous region, in continuous zone, we may have a little bit high torque here, and then it starts dropping, and it can then we can expect the fall as the peak, as then it follows almost the peak curve. So the curve we can adjust per as per our design, how we design the shape of this curve. Majority of the shape of the curve will be same, but what we can do is we can push this up, or we can push this up here in this direction. And there are other requirements, like you can see, read out this here on the chart while while I'm talking. You can see these other requirements, and the cycles also we have plotted. Earlier we have seen that how we can now say we know now what kind of a power we need, what kind of a torque we need. Now let's say that we have two machines, or we have say suppliers of machine, or we have say catalog from the supplier, and they have this kind of a machine. Because we are at a very early stages, we are just finalizing or deciding some of the key specifications. So we have these two machines, and we have to select, okay, which one to select, because both are almost having the similar power. So you can see the torque for this machine is very high, but the speed is very much limited. Here we have a high speed machine, but low torque, right? So so we can we do something here with the help of gears. Okay, we can take this machine and boost the torque here, amplify the torque here for whatever the peak operations. Okay, so the gearing is also coming into picture when we start looking at the machine, which machine we are selecting. So at the back of mind, the system integrator or a system person has to keep this continuously referring to the gearing that those are feasible. So the high speed machines especially is the trend, because those are the volume of that machine is less, mass is less, and if the mass and the active material is less, then definitely it will impact on the cost as well. So it is a trade-off between gearing and machine. So if you try to reduce the machine weight or cost, then maybe you need a better gearing. And then again the cost and efficiency will come in picture for the gearing. So this kind of a studies we will now start doing. So let us assume that we have many machines like this kind of a curves we have from the machine. Okay, sorry. I think there is some
Yeah, Ashish.
bandwidth issue. Yeah.
Yeah,
Mm.
continue.
So so let us focus on some key two extreme machines. One is very high, say 44 kilowatt. Another is say 80 kilowatt. And then in between we have some selections. So let us see how we can decide. So let us consider one example here. And I say example. Strictly, it's an example. There may be other elements to consider here, but just to give a flavor or what kind of influence it will have. Let's say one of the stringent requirement that you have, maybe acceleration. You need to be, say, vehicle has to be very competitive in the market, and then say you need 5 seconds acceleration for say 0 to 100 kilometer per hour. And we can do this in say 1D simulation, and you come up, say this particular machine is giving us the meeting us our requirement, which is this red color. So this is the speed that you can see on the this axis, that 0 to 100 we can achieve in say 5 seconds. Now the good thing that you can see, it's a very interesting thing to note, that this particular machine is this 80 kilowatt machine here, which has low torque. And as I mentioned, if we talk about acceleration, we are focusing on this big torque here. And maybe we may assume that higher the peak torque, better is the acceleration. It's not the case always. We have to be very careful when we pick this, because you see the other machines are very fast, okay, but they start dropping the speed because they are not able to sustain that acceleration. So they are very quick during initial seconds, and then after few seconds they cannot compete with this low torque machine, which you can see the base speed that we call here, from where the torque starts dropping. This corner point is called base speed. So the base speed of this machine is very high. So you can see the accelerations are sustained here. So there can be such elements in your design, and we have to consider all these elements before we make any decision, or we go with some kind of already decided, like, okay, we need many times we consider the better the peak torque of the machine, we can pick that. That is the best thing that we can do, but it's not the case here. So we can see that we have to be very say cautious when we pick any machine and gearing, and we have to do complete study when we do such kind of analysis. We cannot just look at the requirements and the machines and the catalogs, but we should have some model ready, some approximate model ready of the vehicle to validate such kind of a claims or such kind of a requirements. So coming to the gearing now, so because that is a well associated with machine, so we will go in detail later for the gearing, but as this is a very close to the machine topic, you can see with gearing we can boost the torque. But if we have two speed gearing, we can take advantage for increasing this top speed. So vehicle performance, if you want to say 120 kilometer per hour as your top speed, then you can say, and you are getting say 100, then we can do that with a second gear. So we can have these day, I mean today we have a one gear, say mostly one gear system for the passenger cars and other cars. So that suffice most of the requirements, because as I mentioned, the vehicle characteristics, I mean the electric machine characteristics goes well with the vehicle requirement. But you can enhance and you can optimize. We'll see how we can do this optimization later, or what benefits we get out of it. So there are many things like two speed. There are Twinster in the market, like GKN has got two Twinster in this. Multi-speed transmissions are coming up. So what elements we should consider? Weight, cost, efficiency, because the more gearing we have, we'll have weight and efficiency involved in this, right? Volume, cost, and how much we can really reduce the size of the machine if we go for better and better gearing. So all these are the trade-off studies that we can deep dive. This when in some other sessions we can deep dive this each element and see we can take some cautious decision with all informed decision, we say. So let's see how we scale this. This all this whatever the electric drive unit or whatever components that are evolving for the electric vehicle, they are moving towards the modularity. So the more modularity you bring in your components, the lesser cost that OEM or other people has to bear, or even the tooling and other things also get reduced. So can you scale up your design? That is a question always that anybody tier one or OEM will ask. That can we? What kind of a scale up is available? So if we look at this machine, and this question will be for anything, for inverter, for battery. So this modularity is everywhere. I'm just taking here example of machine. So from modularity perspective, there are two key elements that we can play. One is this diameter. So this is a torque equation. This is a generic torque equation. Okay, there are some specifics of torque for related to machines, but as a high level, we can consider that torque is function of diameter square into the length. So there are some modularity. There are some modularity in the market which plays with this length because it is easy to play, right? It is easy to change. You just keep some stacks ready and you just assemble those to increase the length of the stack, and you can deliver more torque, isn't it? So that is possible, but the thing is, the more length we have, the losses will increase because our electrical resistance is a function of length also. So there is a limit to that, and then we have to consider the D. And the diameter, when we consider to increase, there will be tooling cost involved, punching. We have to punch new lamination, different laminations. So the tooling cost, the manufacturing cost goes up. So when we increase the diameter, but there are situations where you can't help with, because simply increasing length you can't bring modularity. So you have to consider some moderate diameter, where you can downsize and you can upscale it, or downside, say, degrade it to the lower performance vehicles. So this is a critical decision for any, say, component manufacturer or a tier one or a OEM, that which vendor I should go with, which vendor will bring flexibility. That is what they will be looking at, so that I can plug and play some, take this machine out and put that another machine. So this is a modularity consideration that it is, and it is a sustainable, right? This is only going to sustain if you are offering solutions or something to the OEM, and if they are really thinking about this kind of strategies, they will definitely look for long-term solutions and partnerships with you, which can sustain. So the another element is the constraint. As I mentioned, we will touch upon some battery side because that is where power and energy coming from. So when we talk about this electric drive unit, the battery is also is also playing key role in shaping up this torque speed curve. So depending on the C rate, the battery also has such performance curves, like how we have torque speed curve. There we may have SOC curves, okay, with temperature, or the power curves, like how much power we can get for particular SOCs, how much discharge curve, charge curves. So based on that, we have to find out at particular VDC, say 60% SOC or 50% SOC, which is a, say, average SOC of the battery, what VDC available for the machine. That is the average, because that is rating that we can call, and that is not the actually a stagnant point. It is variable, but somewhere we have to rate. So we typically OEM go for 60%, 70% SOC region, and then at that point see what C rate we have, what current we can get from the battery as a discharge, and what voltage we have at that particular discharge. So for example, we at peak we discharge close to, say, 4C, 3C kind of a current. So 4 times the rated of the 1C, whatever we have for the battery. So say for example 100 amps, that 100 amps is converted into torque, that is directly proportional to the torque. So this particular piece is defined by the limitation of the battery, and this particular point here, that is corner speed, or somebody call base speed, this particular point is defined by the VDC, okay, that the voltage coming from the battery, which is converted into AC through inverter. So ultimately it is a, from battery perspective, is a VDC, that bus voltage that will be. Now what impact will have on it from inverter on machine, or say as a electric drive? The better the modulation strategy we have, you can see we can enhance our curve from some this orange color to black color. So we can see the torque is increasing from one modulation to another modulation. But can we do this at what cost, what harmonics, what kind of challenges we'll have at that for that modulation? Can we change it? So those all detailed discussions we can do when we talk about this in detail. But this is something that modulation index or modulation strategy is this something key parameter from the machine or from the even the complete electric drive perspective, and that is what is going to impact the vehicle performance as well. So available current voltage switching strategies, or I will say modulation strategies, all forms the design space for the complete drive. These are all the driving factors, key driving factors for this design. Another element that I want to bring in is the architecture, high voltage architecture. That is also that also influence your design. So what architecture a vehicle has got, say for example here, many vehicle doesn't have this DC-DC boost converter, bidirectional boost converter, but Prius has introduced this. It drastically brings flexibility, changes the architecture so that you can have less say less terminal of for the voltage for the battery. Terminal voltage will be less for the battery, but VDC will be quite high. So now this also influence a lot on our say design space. So we can what we can do is also look at such kind of a detailed architectures like this, how it is going to influence our design, what elements we should consider. When we do deep dive, we will be when we do deep dive sessions, we will go into these kind of a detail of parameters or details discussions. So the terminal voltage, when we reduce, what will what will happen with the battery? That is also something very interesting. If you note this and you are keen to work on battery, this is something very interesting discussion can happen on this when we reduce this and we have this. But when you have any other element in the architecture, we have to consider its efficiency, because these all efficiencies are going to multiply. So we have to see the maps of the this particular component as well when we talk about such architectures. What this benefits us if I have more VDC, as I mentioned, the corner speeds. It helps me with the corner speed, right? Because your back EMF, you can have your you have a very good margin between back EMF and the available terminal voltage, and you can push ID and IQ more and more. So IQ element can be more, the current can be more, to have more torque. So the this also challenges that can we have such architectures, variety of architectures which can bring flexibility, so that if in future something changes in our vehicle, some technology changes, can we bring in those elements? Are we our is our architecture flexible enough? So there are a lot of elements to the architecture flexibility and its impact on the electric drive. So we will also this is just to give you an idea. If you are interested to deep dive this individual topics, we will be going through a later stage. So VDC available is very important. Architecture, what is architecture? That is also another consideration for the machine or in the drive side. So what are the prominent in machines? Induction and interior flux machines, interior PM machines. There are other categories like wound synchronous machine, there are axial flux machines and blah blah blah, but those are still they have to prove a lot. And the matured, well adopted, well commercially available, these are the two machines. There are other full lease like SRM, other machines, but those are either less adopted, or those are in early stages, or those are not very mature technologies, or those are not, we have to test and try. And there also is a challenge, there is an opportunity to have more types of machines here. So what rotor topologies we will have is like a SRM, you can see this kind of topologies, and IPM is something we call interior permanent magnet. The way we play with the arrangement of these magnets, we get more and more torque density, power density. So these are very critical designs. Rotor designs are very critical from machine perspective, because you see this machine rotor is also limiting your maximum speed. So you have to we have to see, we will see in when we do some deep dive, we will see which part having more stresses, mechanical stresses. So which part will fail and what limitations come from the rotor design when we talk about the top speed of the vehicle or maximum speed of the machine. Then coming to the stator, stator is, you can see there are a variety of winding strategies that you can implement, and they can help us not only reducing the cost of the material, active material, also they can help us in say fast manufacturing, quick manufacturing, chain type windings, or maybe reduce some of the key harmonics which is a loss in the vehicle. And any loss in the vehicle is a so much penalty across the vehicle. It will put penalty on inverter, it will put penalty on the battery, and the harmonic or the losses, or I will say efficiency, these are all on similar lines. The each harmonic that we are reducing is going to be significantly helping us either reducing the weight of the battery or increasing the range of the vehicle. It's a very critical elements that we have to look, and when we deep dive, we'll have to see what elements, what harmonics inverter brings in, what kind of reduction is possible there, what kind of reduction possible in the machine, and all those things. So here, depending on the machine winding strategy, we can really decide about the harmonics. There are two specific in permanent magnet machine. There are two topologies that I see. Like you see permanent surface mount, and there is a interior. These are interior permanent machines are the most dense. Power density, torque density is very high, because they bring some saliency. These inductance, when you have these unequal inductances, there is a extra element of torque that we get, that is called reluctance torque, and that extra torque actually help us to improve the power and the torque density as compared to the surface mount, where these two inductances are same. So we can go through this when we talk about some machines in detail, but this is a high level consideration that we will have at this moment, that IPMs, why IPMs are popular, because they bring this kind of a the advantages. These are some of the advantages. There are some disadvantages with permanent magnet. There is no technology that you can adopt. There are trade-offs, and engineers has to work around that trade-off, right? That is how it is. All the any thing that works. So here, when I say pick this machine, or we don't say pick any other machine like axial flux, there are other trade-offs that we have to study. There are other challenges, but I am not saying that these other machines are not good. They are good. There are other challenges with that. But IPM is something that is where people are, that is why I focus here. There is where you see more adaptability. Now, another consideration when you talk about machine, how many poles, what is the speed, how many poles we need, 6 pole, 8 pole, 12 pole, because this is where now inverters start kicking up. Inverter, because the more poles you have a very good speed. It's a high speed machine. You can really reduce weight, because you see the back iron here is reducing. When you go for 4 pole, you see the flux lines, dotted flux lines. You need much more material on the back side of the, and your OD of the stator can be much higher to allow this lines, flux or magnet lines to pass. When you go for 10 pole, you see you need you don't need this much. This is redundant. You can cut these laminations here, and you can still have very less OD. But when you start doing this, there is another element, that is a inverter switching frequency, because that as you move this side, we have to, and the moment you have more higher switching frequencies in inverter, other losses will increase. The switching losses will increase. So we can see there is again trade-off here. So we cannot just keep on increasing poles to have very high speed machines. So this is another trade-off that we have to consider, and this is a key consideration by the way. Many people just go and buy some drive unit, but we have to know what kind of know how many poles are there, because this information you have to put in a controller. When we will talk about controller, this all characterization of machine has to go back to the inverter or the controller that sits on the inverter. So we should know many parameters. We cannot just be just buying this kind of a stuff. There are another thing that goes into a controller: the highest amount of current that machine can handle. That is a demag current, IDMag. So demagnetization happens when you push large large current in the machine. The especially the direct axis, D-axis current, it is demagnetizing the magnets so that you can increase the speed. So it's called field weakening zone. The moment you start doing that, you are shifting this whole this magnetic operating point in this direction. Okay, and this is a demagnetization curve, and at certain point it loses the magnetism permanently, so you cannot, or partially. So there are some partial demagnetization studies that is being done in case of fault. Okay, so when fault occurs, we have to limit our short circuit current. So I don't know whether you, as at a vehicle level, we have to do when we talk about some other deep dive sessions, we'll do how to calculate fault levels. Fault levels across the vehicle, which fault levels are more, how to put fuse, how we should have a protection system, how to have a coordinated protection system. All those things will be control strategies will come into picture from this point. So see, you have all these interlinks. From machine side, you are going all the way to the controller side, all the way to the fuses and other side. So the from the winding topology, you have many variety. I mean, this is just to give a two major: distributed winding, concentrated winding, hairpin winding. This is another winding that is becoming popular. So what kind of a winding strategy we should have? This winding strategy also directly impacts our thermal cooling that required, whatever cooling is required, how effective the winding is to cool it, how easy it is to cool, what are different heat transfer coefficients involved in the end winding cooling. So these winding strategy also helps us to reduce some end winding material, reducing the copper in the winding, and ultimately this broadly shapes the speed torque. Because your rotor combination and the winding combination is what is the speed torque, right? And what the steel, that active steel that you have. So these are all, we are playing with active material here, which will directly impact on the speed torque and efficiency. So there are many other windings. These are like fault safe, fail safe, because there are many times we need fail safe. When vehicle fails, there are at least if two phases are available, and if there is a less mutual inductance between the two windings, or three windings, then we can have at least two winding and some torque to push the vehicle or take it aside, or pull aside somewhere in a safe area. So that, as I mentioned, harmonic is a key thing, whether it's an inverter or a machine or whatever the system that you are working. When it comes to the power electronics and machine design, it's harmonics is that what we will be deep diving in our other sessions. So here is just I'm giving you a flavor that 5th, 7th, 11th, these are the very bad elements, and few elements also produce reverse torque. So torque reduction will happen, and these harmonics are nothing but loss. It's a I square R that you are directly putting, which is very high frequency, which is and it is very difficult to eliminate because these are not so high frequency. At least we can have some filters or something we can do with, but low frequency is not that straightforward. So we have to play with some slots, some winding, some arrangements. So some slots and winding arrangements you can see. So here is a air gap flux density that we keep on looking when we talk about any machine. Okay, so if you do FFT on it, fast Fourier transform, you can see if I change the winding topology, or say some slot designs, you can see from conventional to some specific winding, we can reduce this windings, and some specific winding arrangements can even eliminate harmonics. Some the cost function is there, so if you put some angles there, cos alpha, you can even make it zero. Some elements may, some harmonics may disappear if those are, and these harmonics not only lost, but it also giving a lot of low level pulsation in the torque. So this is something we will be focusing more when we talk about the machine or inverter. The losses in the machine are copper and ferrous. There are a variety of losses you can see here, but copper and iron losses are something very important. And when I say losses, it's a efficiency. So these are the two elements that are impacting our efficiency of the machine: copper and the iron loss. So this efficiency it looks like this. This is a typical. This is not a specific general curve. You can say this is a. You can see the efficiency map is more here. So more the darker color on this side, it is better efficiency. So what our aim or what our target is to push these boundaries. This is what our aim is always consistently, and have better and better efficiency zones, so that we can really optimize our machine where the drive cycles demands. So this is where all integration comes into picture. If you buy this as a ready-made element, you may not be able to do this kind of studies, and I doubt if you supply tier 1 will give such kind of a great details so that you can do this kind of a study. So the thing is, tier 1 across globe, barring I don't know in India, but other in other countries where this is being adopted, they are bringing a lot of designs in house, or they are closely partnering with, or they are redesigning whatever they are on the off shelf. Off shelf is not right approach. They have understood it's an expensive thing, and to sustain they have to do a lot of partnerships. We'll discuss that in a later stage, but this is where this design is very important for us, because that brings a lot of opportunity to us. So the electric performance is electric machine performance, not just motoring, whatever I am showing you, but also regeneration. And this torque, speed, efficiency are for particular point. Okay, these are for particular cooling limits. Okay, say some conditions, like at some ambient temperatures. So we may have variety of such curves at different conditions. So you can see the machine, if you look at, it provides very high torque for a short duration, like 10 seconds. Then as we increase the time, it starts dropping, and there will be some typical coolant temperature. Also, we have to consider the best voltage range that machine can perform. So voltage, it's going to vary, isn't it? That the corner point which I mentioned, if the battery voltage start dropping, this also start pulling here, right? So the thing is, we have to declare, okay, what is the best zone or where it will start deteriorating the performance. From system perspective, this is very important, and this is called voltage stack up study that we do. Coming to the cooling. So the cooling is very important, and the end winding you can see is something critical that you have to cool. And these are the cooling channels around it. So I will just show you one specific video from Audi, which they have. So you can see stator here, the transmission on that side, the rotor here on this side, and there are housing which carries these cooling plates or cooling channels. So these cooling channels will have glycol plus water running inside, and they have improved this design, and you can see the rotor is also cool now, not just the stator, because even rotor has got many losses, like eddy current losses are happening on the permanent magnet. So the magnet temperature has to be, because the demagnetization is also a function of temperature. So you can see there are two designs that they are comparing. This is a old generation and this is a new generation. So you can see the rotor temperatures are much better. It's blue color, it's a red color. So you can visit this in detail when you have time. You can see this very nice video for the cooling. So the torque pulsation, now vibration. So we do a lot of skewing of the magnets. So in IPM, we have to do this kind of arrangements to eliminate or reduce some of the harmonics, because in low cost we may not see this kind of a thing, but for two-wheeler, for three-wheeler, I don't know, those may be straight, and you can still have to afford afford those kind of vibration, but in other vehicles or some expensive vehicle, we have to work and provide some skews on that. Now this pulsation and vibration, not just from machine, but it will come from the inverter also. What PWM strategy we have, what kind of a switching we are doing for the PWM, what kind of a harmonics, what is a switching frequency we are using. So you see here, the when we talk about just machine, we have touch base on almost all elements, inverter, gearing. So very less now available for the individual components as such. But I started with machine, and you can see it's all revolving around that. And now let's go to the gear. So the gear, if just one example here is from the bolt, which is again available on the net. You can see this, and this is the rotor, and there are inside magnets, which is, and you can see the how the final FDR, that we call final drive ratio, that how it is getting calculated, and it is how it is connected. It is much simpler than hybrid, isn't it? The hybrids will have, say, a lot of other elements like DCT and other gearing and long transmission, and then those. But here it's becoming simple, very less rotating parts as compared to even hybrid or even IC vehicle. So it's becoming really, and that also helps in efficiency, isn't it? So there are many other topologies in this within gearing, but what for us, what is important is how we optimize this machine with machine, right? So say our target is range, our cost function is range. We want to optimize our cost function, and the range is our. There can be other parameters. So you can see this is the ratio on the x-axis, and y-axis you have a cost function. So one is better. So we can see the range in blue color, which is better when we pick, say, 7 ratio, 7:1 as a gear ratio. Now if we want better acceleration, say launch, we can see 9 maybe better. So this is a trade-off optimization that you can do, trade-off analysis you can do. You may have different influencing parameters that you can do in this study. And then another element to this is vibration, because when you put this rotor slots, gearings, all these together, they also have some interaction, model analysis. They have their own frequencies, natural frequencies, and then they have their own harmonics. So all these will have impact on noise and vibration again. So what housing we have. So when we talk about this complete noise analysis or vibration analysis, these all we have to consider. These are all the vibrations we can. So when we do this deep dive, we can talk about what which one, I mean, which component is predominantly generating this kind of. So we can analyze these plots and try to figure out the sources, which source is contributing more to that vibration or say noise. So you can see here, I am taking some software example, which is from this. You can see at the bottom the references. So we can do some interesting study like across torque speed curve, where are the more pulsation, and obviously, as I expect, you will have challenges at higher speed, right? Those harmonics, and that is quite obvious at that. So you can see about what level, that is the quantitative analysis we have to do. So coming to the inverter, so we have covered these two, gearing and machine. Now inverter, again here parameters for inverter are almost same. It's efficiency, switching frequency. Higher the switching frequency, better it is, because we can eliminate some harmonics. but also it increases losses. So the thing is, there is some technology which is called silicon carbide technology, the switches. So instead of silicon IGBT, you may use silicon carbide MOSFETs, which are much better in terms of power density, in terms of switching frequency, and this WBG overall, even the GAN you can consider, but SiC is quite available and commercially there. So many people or many OEM or tier one are offering this kind of a solutions already in the market. Not many vehicles with SiC, but there are in the market, and soon. So this is a trend. We have to catch that trend. Otherwise, can we have flexibility with this, or we should have understanding what kind of a technology the supplier or tier one is offering to us, whether it's really in line with what the future is, whether they have any consideration for such kind of a technology. So all this, and what switching losses, what densities, all these kind of when you go for say OEM meeting or a supplier meeting, all these topics will come up and we can discuss on these topics. These are all high level parameters that we have to. And then stacking, that is another thing that is coming up, or it's already there. Inverter stacks are there, so that brings a lot of modularity. The inverter also impacts on the machine, as I mentioned, and SiC especially is also helping not only inverter as such, but machine as well. So you see, if I adapt SiC, the overall harmonics also reduce because we can do better, adopt better modulation, and it reduces the some losses in the machine as well, because you see, compare these two, one with SiC, another. There are other challenges like with SiC, because these are fast, they have more DIDT, right? There will be insulation stresses on the machine, so we have to consider some of the high voltage stresses coming due to the high switching speed, because those are very high in microseconds. Those ramp up will be there, DIDT will be very high, so we'll have voltages accordingly, and those the creepages and all those we have to address when we adopt this. But it gives good it gives significant advantages, even if we can say. Modulation is something key thing. So 6-step is like it's like a key thing, which from where many other switching modulation strategies are developed. So these, once we understand this 6-step, basic 6-step, the FOC, the space vector and all is very simple to understand, at least understand. I'm not talking about implementation, but at least we can have better understanding. So this is a 6-step. That is how you can see the, this is a magnetic MMF vector. Okay, so if in space vector we have a very smooth rotation instead of those kind of pulsating 6-step. So there are advantages with 6-step. It's not that that is a very poor way to do, but that has got some advantages of available voltage VDC, and this also has got some advantages. So this like low harmonic. So space vector modulation is common. Now coming to the control strategy, motor, machine control, or drive control. So the thing is, we want this all our AC machines to behave like a DC machine, so that we can control it very easily. So if you know, DC machines are very easy to control, whereas AC machines are little poor, or it's not that easy to control, and hence this field oriented control or the heavy mathematics that we have to deploy on the controller of the inverter. So on inverter this sits this control algorithm. And what we have to do, when you say, now many people will say BLDC, is it a DC? No, it's not a DC, it's a AC. So when I say DC, DC is a DC machine is a where we have a brushes and other commutator and all those things, right? So we can't use those kind of machines here, even though they are better for control. But for here we all need BLDC kind of a PMSM. BLDC may be low cost this thing machine for maybe two-wheeler or something. But for PMSM, IPM machines, these are the control strategies that we all have to implement. So this is nothing but a mathematical implementation. So what it does, it takes the three-phase current and make them mathematically behave like a DC. So you can see these like ID and IQ are like a constant current, like a DC current. So through some mathematics transformation, Park and Clark transformation help us. So Park and Clark, those two people help develop this mathematics to come from this rotating reference frame to the this to the from say stationary reference frame to the rotating reference frame. So you can see here this is a stationary frame and this is a rotating frame. So rotating frame is as if we are jumping on the rotor and looking at the observing the field. So you can see the field from there like this, like ID and IQ. So that now we have two components: ID, that is a field, say the speed, flux control, and IQ, which is a torque control. So if we can control speed, that is flux, and the torque independently, then we can easily control this machine, and that is what the principle of FOC. So the you can see at inverter level, these are all the software and everything will be implemented. So all the resolvers, these ADCs, all those will be implemented. The resolvers take the theta angle, then two phases will be sensed. Those will be converted to Clark Park, inverted, and we have PID controls here. So all these control strategy, if you want to understand in detail, we'll have deep session sometime, or you want to implement this somewhere, we can have these sessions. So this modulation or this strategies help us a lot, okay, in terms of adopting make changes in the torque speed curve, which directly impacting our vehicle performance, and do some harmonic analysis. You can see there are some low harmonics in the inverter. Here you can see in inverter only high frequency harmonics are shown, but due to the date time and all, we have to consider all these say fifth and seventh harmonics as well. But it is for if those are high harmonics, it's good, like we can have some filter, so those are not really worrisome, but low harmonics are something we have to get. So and in IGBT, if you open the module, it will look like these bond wires are there. We can deep dive again this when we have time. So the cooling part is we have heat sink here, and the critical is the junction temperature. We call that as a IGBT or whatever MOSFET junction temperature. It's not directly measurable. We calculate that based on the different algorithms, and then we have this cooling channels here. So we are moving in SiC and GaN technology in inverter, and that is where we have to keep watching how the suppliers tier 1 and also the OEMs are. The key element, as I mentioned, is the system efficiency, and there are the more components you bring in the powertrain, they are all they are all the sources of the losses. So you can see, if I consider even charger, while charging, it will bring its own efficiency, and the thing is, these efficiencies are not same for say if you see torque speed efficiency of inverter, torque speed efficiency of machine, they are not same. Sometime machine is operating in very good efficiency zone, inverter may not. So we have to match those. Okay, when we design this, we do this kind of a deliberation to map these. As a system level, we get very good efficiencies considering the drive cycle, most of the residency that we have. So if you see, if you study this is a little bit old chart, but it gives a very good, still it is valid, that various manufacturers are relying on water glycol mixture. Okay, so there are other technologies that are emerging, like some immersion, dielectric cooling and all those stuff, but by and large, as per the commercial availability is this. You can do the research and opportunities are there for other types of liquids. Now the question is whether we should have motor first or inverter first in thermal circuit. All those elements we will design when we deep dive this. Okay, based on the heat transfer coefficients or the thermal resistances. So the other element is whether we should make or buy. So this is again little bit old chart, but you see 50-50%. But now if I update this chart, which is a bit, I am a bit lazy to update, but this is just copy pasted. Most of the people, not in India but other countries, they are trying to bring many things in house, because that is where the costing, control, and the better efficiencies, reduction in battery. So when I say bring in house, yeah, there may be people, partnerships, but they are close partnerships, not off the shelves. Okay, off the shelves are not the, you have to do a lot of customization. If the supplier and everything is ready, then you can do it, and it has to be very close and no, specific to that OEM. They have to open up everything. So there are other elements which I have not touched upon, but here worth considering, which I'm just giving you a glimpses, so that you have better, or it triggers you the further thoughts, and we can deep dive that in some other sessions. So we'll have some deep dive sessions for some specific areas. So you can see in thermal circuit, whether I should put machine first, whether my radiator, which is a say low LTR, we call low temperature LTR, should be front. So there will be three thermal circuits, or two thermal circuits, and they are interlinked. So we can have very good thermal considerations for these kind of studies, where, and those are very effective. How we should place these radiators, how is the airflow, the component placing. The other thing is, what if switches fails in the inverter? What we should do in such condition, whether the machine can sustain this, protections, location of sensors where we should have, then thermal constants, as I mentioned, the cooling strategy, peak versus continuous, how it impacts. We have not very deeply discussed this, but this is worth of a 2-3 hour discussion. Then torque and acceleration, which will limit. What is a bottleneck? We have to see that as well when we scale up or scale down. Repeated acceleration is a key thing. It's coming into now battery and machine both in picture. Who will put the thermal limits first when we do repeated acceleration? Sizes, typical sizes, what kind of a sizes we expect in say in this domain. Then high voltage, so 48 volt, 72 volt for passenger may not be good thing to continue sustain. Across globe it's increasing to 400, 800. Taycan, all those vehicle, if you see, those are having 800 volt the power train, by the way, not the just the charging. So charging with 800 volt will be 15-20 minutes if the battery allows, but right now people have already reached to the 20-25 minutes with the high DC charging system. So we have to see what kind of a safety that, because each person has to do some certification before this he touch above 60 volt. So 60 volt is something okay to handle. Above that 60 volt DC, it becomes hazard, and it may be we have to go for some regulations or certifications. So those are all high voltage challenges that we call. Some safety we have to understand how to handle those. So these are all parameters that you can have no thought, like optimization, as I mentioned, NVH, and the off the shelf, picking off the shelf inverter, you have to give serious thought to it. And whether my supplier or my tier one or whatever, can I get some open access to the controller sitting on the inverter when I buy, if I buy. So how much weight, battery weight I can reduce if my efficiency increase by blah blah number. So we can do all these very detailed calculations when we deep dive this in a workshops. So the DOE has already put whatever I put this mention these challenges. They are also thinking to increase this. I mean, this is where all this is coming into picture from DOE as a direction. We are all trying to increase the efficiencies bands across the speeds. So that is where you can also, this is an opportunity for us, and reliability, bring the reliability. The lowest reliability or lowest link is inverter. So how we can make it more better and better from reliability perspective. Cycles of batteries, all these are consideration weak points that we have to consider. So this brings a lot of opportunity. Now I think you might have guessed a lot of opportunities in this area, or you may be knowing but I'm just listing it here for you, which comes to my mind. So it's a multidisciplinary domain. It's not like something one expertise you can just work and just get rid. This is a multi, you need mechanical integrity you have to address, right? The electrical aspects you have to address, cooling, thermal experts, CFD experts you need. Huh? So all people come together, and then they can have this kind of challenges addressed, and that is where is opportunity. It needs all the time system approach. Somebody should be there to always guiding, giving this system view. And this brings a sort of research and development, and many people, many matured OEM, I will say, they are not doing themselves all this everything. They are partnering, they are bringing in house, they are trying to bring some fresh minds, fresh new people who has this expertise, because they are all sitting somewhere else, and they are doing some partnering. So they need, their challenge is to pick right people, because they need to have right expertise, not just the vehicle level, but those who have right deep knowledge on these components, and what future will be, what trends will be, because that is where the flexibility will comes into picture. Because once they invest money in one particular technology, they should also see if I can encash with changing technology in coming future. So off the shelf is not, it's my personal, whatever I see, it's not a sustainable solution of the shelf. This is something we have to, one day we have to give a serious thought to either partner or no, do some changes on our own, or go for some open platform where we can change some parameters. So that's the end of my technical content delivery. I just want to announce here, take this opportunity to the courses that I will be doing with the device. So Shekhar has given me this, no, the opportunity to work with him to offer this kind of a courses, and this will be delivered by say me predominantly. Whatever I am showing, there are other courses which Shekhar is also going to cover. But I come from these other, I mean, this I work for Jaguar, Land Rover, Ricardo, and other Rolls-Royce in various countries, and I come from, say, battery and other this electrical electronics domain, work on variety of areas, and you can see that this can be the lectures what I will be delivering may not be a bookish kind of a thing, but those will be very practical, and whatever I have seen, experience sharing. So if you are involved in, say, product planning, decision making, or some architecting, this may be the course. Like it gives very deep system view, each component and how the system behaves, and how battery calculations and how reduction in the battery happens, charging limits, battery limits. If you are working deep, like on 400 800 volt systems, if you plan to do so, I have certifications from the regulations that I can certify people to work on this. There are some processes that we have to follow across the industry. We have to implement this with very some displays, with some care. So we do certifications. We can do these programs for managerial level, for those people who directly work on it, because manager has to sign some cards. So there are some processes involved. If you are planning to work on deep on, say, energy storage as such, not just the lithium ion, but some supercapacitors or a hybrid energy HESS that we call hybrid energy storage systems, or like some ASIL certifications you are going for, then we can help you to understand this better from the battery, what these each parameters. So there are 4 modules. You can either pick individually, or we can cover this in an entire session. And it's all you can see this in books, but how this actually gets implemented, and what are those challenges in implementation, we can discuss those in these deep dive sessions. If you are a power electronics guy, like you are interested in power electronics, we can I am covering some inverter designs, or some high level. If you want, you can customize this course. We can talk about some capacitor sizings, how we can do the, because that is something to do with Ripple and their cost. So we can do onboard charging. We can cover that, because once we know power electronics fundamentals, we can talk about by and large these components, converters specific to the electric vehicle. There are other, a lot of other inverters and strategies on we will focus on what is being implemented and what is there in existing, say, vehicles, and those things, and what is coming. So the as Shikhar mentioned this in mail, this whole thing, that all content we put together so that we can contribute to the COVID, to raise the COVID fund. And if you wish, you can pay some token amount to, or some amount to the method mentioned by Shekhar. He will be, he will share. And the he will also share the feedback with you. And I really thank you for investing your time and spending time with me. And it's my pleasure to share these whatever I could present in 1 hour or little bit more. This is actually my pleasure. Thank you, listening this patiently. Shikhar, uh, over to you.
Yes, Ashish, thanks a lot. I'm sorry we had some hiccups in between, but overall we tried to complete on time. So I'll quickly try to take a few points before we get to question answers. So first of all of you coming out in large numbers for the webinar kind of just proves that the future is of mobility is headed towards electrification, and the key challenge is going to be to develop a optimized vehicle. Optimization has to be done for the battery. Optimization has to be done for the motor and driver, as you saw today. Optimization has to be done for the cooling architecture, and optimization has to be done for the entire electrical layout. And towards the same, we are launching a course, which is a certificate course, which is called ASME. So, Ashish, can you go to the next slide? So, this course is titled Advanced Systems Methodology, uh, where we are going to work through the hardware selection, sizing, additional features that the vehicle needs to have, the industry trends, and how the supplier should be selected for particular components. So we do cover all of these elements, and you are doing your own thinking. So we are just guiding on the steps, and you are doing your own thinking during this time. Uh, Ashish, next slide. So this program is applicable for students or recent graduates, industry professional already going down the path of e-mobility, startups and suppliers, as well as anyone interested in doing this subsystem level optimization. So those are the key beneficiaries of the program. Next slide, Ash. And as I said, we'll be covering all the system level calculations, the battery pack, the drive motor, and the charging systems. So along with that, Ashish, next slide. The electronic selection, BMS, the motor controller, the VCU, the wiring harness design, validation and testing, what does it take to get a regulatory approval, and using all the simulation tools that will be undertaken during the course. Obviously, given the current situations, this will be rolled out as an online offering, and we'll also cover some elements of the IoT and autonomous technologies. as well as what is happening in the industry. The course will end with a case study, assessment, and a certificate. Right. Obviously, as I see a question about placements and jobs, ideally we would like to offer the placements. Given current scenario, I don't think anyone can say anything. We don't know how the companies are going to come out of the current situation. So overall, in terms of the course, it is 10 days of work altogether. Professionals can take it as per their schedule. Students can take 10 days in a go. The effort is going to require you to put 5 hours in a day, and we will be sharing a registration link, and pre-reads will be given in advance so that you get some time to prepare for the course. The course is planned to start in the first week of May. Next. So right now, the program fees as a discount to people who have attended the webinar, we are giving students program fees of rupees 2,999, and for professionals 7,999. The link to the pre-registration form will be emailed to you post 2 o'clock today, along with the feedback form.